All right, so the next topic that we're going to talk about is arrays and linked lists. Now, in some ways, they are basically data structures that are building blocks for a lot of things. I don't think these concepts that we're going to talk about are going to be completely new to you. Take it as a kind of like a refresher, but we are going to start to emphasize certain concepts and practices that we do inside CS201 that may be relatively new to you coming from, let's say, your previous programming courses. And that is in terms of looking at the efficiency of things. Okay, so let's start with arrays. Now, what we talk about when we talk about arrays, we have several concepts in mind. All right, so their arrays are defined as a fixed size sequence collection of elements of the same type. So fixed size, sequence, same type. All right, and this has implications in terms of the way that we store arrays as part of our computers, right? And why is it fixed size sequence collection of elements of the same type? Because for some of the low-level languages like C, we need to know all these things in order to know how much space we need to reserve for that array. And because arrays are generally stored within consecutive address spaces, so in that sense, for us to estimate how much address space to reserve, then in that case, then you need to tell us about what is the element type, right? Is it Boolean? Is it double? Is it float? Because they are associated with different storage sizes. And then we need to know the size, because once you declare the size, then you're going to store exactly that much. We're going to reserve that. And sequence, because we store it in the contiguous space. Now, that goes on to the logical sense as well. So in things like Java, for example, when you have an array, you declare the array. In any case, these three elements must exist. Now, the first element is that it's going to be fixed size. So then either you declare it in the form that specifies the elements inside the array. In that case, we know exactly what the size is. Or you just tell us what the size that you want. So in this case, it says 6 or 5, right? So it's fixed size. The second thing is that it's going to be of a particular element. So that means all the elements within this array is going to be all of type string. This one is going to be all of type integer. And the final thing is going to be a sequence. So which means that if you specify the content of the array in this way, it means that we're going to access them in that particular order. So for example, in this case, 34, 13, 68, 23, 89, 45. So it means that the first element is 34, second is 13, and so on. So we're not going to reorder them any arbitrarily, because we have to follow that particular sequence. Now, this is how you declare an array. Okay, now you can manipulate them, and pretty much manipulating, what it means is that replacing its value, or you can access its value. Basically, you're setting and getting kind of attributes manipulation. Now, if your array is size n, then the index is always from 0 to n minus 1. So we start a count from 0, 1, 2, 3, 4, all the way to n minus 1. Now, anything that doesn't have anything, any particular index that doesn't have anything in it, you set it to null. And in the Java convention, anything that you set to null, I mean, like if the particular object is not being used anywhere else, then it's going to be garbage collected. They're going to be removed from the memory space. Okay, that's a different thing from something like in C, because in C, once the memory is allocated, you need to take responsibility for removing it from memory, because otherwise, then that memory space is going to be wasted. So Java moves on to a higher level abstraction by taking care of all this housekeeping stuff. Okay, so we're going to take a look at one program, right? Just as a warm-up, we're going to take a look at the operation of doing something. And then we're going to see and contrast how it is that we're going to do this differently from linked lists. That is going to be the follow-on topic, okay? Now, let's say we are dealing with a way to keep score. So you have a competition, right? It could be Kaggle, it could be anything else. And in this particular competition, everybody gets a score. And so what we care about is that we want to keep the top K. Okay, let's call it for some number K. In this case, the K is 10. So I'm going to take the top 10 scores, and I want to store it in a particular order, which means from highest to lowest score. Now, if I have more than 10 scores, then I just want to keep the top 10, right? And let's say this is a simple program that does this. And just as the illustration is showing, you can pretty much use an array to do something like this, right? Because what you can do is just to create an array of size 10 to get you the top 10 list, right? 0 to 9. Okay, so then you see the scores are decreasing, which means that we are basically keeping the top spaces, right? Now, if there is a new score that is going to come in, right, then we need to do some operations. If you want to remove a score from this list, again, we need to do some other operations, which we will discuss soon. Now, firstly, right, let's also associate this with a game entry. And a game entry here is a given score. So you need to have the name and the score. Okay, so a game entry is by someone identified by the name and a score value, which is an integer. And then you have the setter and getter, right? Now, this is one entry. And if you want to build a scoreboard, then you're going to specify the size of the scoreboard. And that particular size is specified by the capacity. So in this case, I'm going to create an array of that number of game entries. And that's going to be as much as I'm going to store, right? Anything else, I'm not going to. Okay, now let's say one operation that we want to enable is to add an entry. And you can imagine that in a stable state, you have some entries already in the list, and you're going to add a new one. Now, because we insist on keeping this in a sorted order, which means that when we want to put a new entry in, we may need to make room for it. So for example, let's say the blue one, Jill 740, this is the new entry that we want to put inside. And before that, just before Jill came in, there were already 6 other game entries there. Mike, Rob, Paul, Anna, Rose, and Jack. And it so happens that 740, Jill's score, is between Rob and Paul, right? So that means that the right place to store it is going to be between Rob and Paul. But previously, we are storing this in a contiguous space, so which means that first we need to make room. So making room here means that we're going to shift everybody down by a notch so that we create an empty space where Jill is going to be, right? So that is the process of adding a new entry inside this list. And so if we look at a method of adding this entry, pretty much is expressed by the following code. Now, okay, so the first thing we're going to test is whether or not there has to be any addition to the scoreboard. Because if the scoreboard is already full, right, that means that I need to replace something, or if the new score is not even larger than the one that is currently the lowest in the list, then I need to, then I don't even bother to insert anything, right? But let's say if I still have room in the scoreboard, or if I have a new score that is going to be beating some of the existing scores, then I need to make some changes. Now, the changes that I'm going to be making is that, well, if currently there is still space, then I know that with the addition, I'm going to increase the space by 1, right? Now, then I'm going to start from the end, which is num entries minus 1. So there's the last one in the board. And I'm going to shift everything down by 1, right? So that means that in this case, I'm going to start from the end, and I'm going to take the last one and take the previous case, right? Which is the previous element. So this is essentially what's happening here is that we are going to be shifting down the line. So starting from the last element is going to take the value of the previous one, and this value is going to take the value of the previous one and previous one until we get to a point where we need to stop the shifting. And so every time we move an element from one place to another place, we call it a shift, right? A shift because we are allocating the same element to a different address. And in that case, by the end of it, we're going to insert the new element into some slot, which could either be the end of the list or is some intermediate step after making space for it in terms of the shifts. So removing it, in the same way, if I remove one of them, for example, let's say I remove Paul now, then I need to remove Paul, and it will leave a hole there. So I need to move everybody up by 1. And in this case, let's say after removing Paul, then Anna, Rose, and Jack can move up by 1. And then the last one then will be empty. So the code that does something like that is given in this slide. And in this case, we see there that to remove it, well, first I'm going to keep it inside some temporary variable because I'm going to return that later. But otherwise, I'm going to start from the location I that has just been removed, and I'm going to adopt the element that is coming right after. So then it's going to be a series of shift up until finally I have gotten to the last one, and then I just set the last one to null, right? So then I can decrement the number of entries. Okay, so now this is to remove it, right? So now let's say if you have a code that does this, then you have a particular sequence in which you are adding things into the list. Then you're going to have the following behavior in terms of when things get into the list, right? So then you're going to get these printouts. Now, for warm up, right? So let's try to do this exercise in class. Okay, let's assume you have that implementation that you had earlier. And what we are asking here is that how many elements need to shift in total as you are entering stuff into the scoreboard using that algorithm, right? And if you can figure out what is a number, and let's talk about what is going to produce the fewest and the most shifts, and how is the number of shifts going to be affected by the length of the sequence, okay? All right, so let's take the next 10-15 minutes or so just to work on this problem, and then we discuss together. All right, so let's talk a little bit about this, right? Some of the discussions that are happening revolves around what is counted as a shift or no shift, right? That indeed is pesky discussion. So that's why at some point when we get to later in the course, we stop being so nitpicky about what exactly are being counted. Then we care more about how things are growing in terms of the functions. All right, so let's take some steps towards that. So let's talk about this particular exercise. And we say the problem is that we have a top 5 score, and the top 5 score is going to be stored within an array, right? And in this case, well, we have the following, but that's 6 now, right? Okay, so then let me just reduce it to 5. Okay, 1, 2, 3. No, it's just 4. Okay. All right. So let's say the top 5, right? And technically, we want to get this one to be the highest one, right? This one is to be the lowest. So now the first element comes in, right? So initially, they're all null. So they're all null, right? That is the beginning of this state before we do anything. We're just declaring them. Okay, so then we're going to start inserting them, and we want to keep the sorted order. So Rob comes in with 750. Now at that point, the only thing that exists is just Rob, right? So then Rob is going to go to the first place, right? 750. There is nothing else there. Now, in this case, what we're doing is insertion. And basically every insertion is counted as 1, right? But let's say when we talk about shift here is defined as change of position. So meaning that 750, if let's say there was a different position and now it's going to occupy a new position, then we count that as a shift. So let's say for insertion, we don't count it as a shift. So then this is going to have 0, right? Because there is no change in position. Now Mike comes, and Mike is now higher than Rob. So in that case, Mike doesn't want to follow Rob, right? Mike wants to be in the first place. So which means that because it's address-based, so Mike is going to go to the first place, and that requires Rob to move to the second place. So that is a shift. All right, so in that case, when we insert Mike, we need 1 shift. And then Rose comes, and Rose is 590. So 590, we still have 3 more spaces here. So Rose can come in without disturbing anyone. So in that case, no shift. Jill comes in. Jill is 740. So 740 is between 750 and 590. So then we need 590 to move a spot so that we can then put in 740 in between, right? Now in that case, this requires 1 shift. And then Jack comes. Jack is 660. So in the same way, we're going to need Jack to, well, we're going to need the previous person, which is, okay, I'm sorry. So that's not, Jill is 740. So the next one is going to be 510, right? Okay, it's not a line. So Jack is 510. So then Jack is just going to go in there without any shift, right? So that's a 0. So now at this point of time, our list is full because we already have the top 5. But we still have 3 more game scores to put in. So then we will look at Anna next. Anna is 660. So in order to get 660 into the picture, what we're going to do now is to go have 590 shift over to 510. So the new one is going to look like this, right? 660, 590, which means that these 3 things stay in place. 590 has to move down a notch, and 660 is going to fill its place. 510 is just going to be overwritten. And let's say we don't count that as a shift because it doesn't go anywhere else. We're just going to remove it, right? So in that case, then 660 is going to account for 1 shift. Okay, Paul, 720. By now, I don't need to do all the shift. You can more or less imagine what's going to happen. 720 is going to come inside here. To make a space, then 590 has to get out. 660 is going to replace it. So that's going to be 1. And the final one, Bob, is 400. 400 is not even going to make this list. So we don't even bother. That is going to get us a 0 shift. So then in total, let's say if we are counting the shift, then in that case, we are counting 4. All right. Okay, so the more important thing here is that you get a concept right. Okay, so whether you're counting the insertion or not and so on, I think that's not so much big a deal at this point of time. But if you're counting the shift, let's say we count 4. Okay. Now, so then the next follow-on questions is going to investigate what are going to be the sequences that will produce the fewest and the most shifts. So we now care about what is the fewest and what is the most. And we realize that what we do in the cases where we are going to have fewest, okay, we have a shift when? We have a shift when there was a score that came before that is beaten by a score that came after. And therefore, the higher score that comes after is going to replace the existing ones. That is a reason for the shift, right? So which means that if I get all the higher scores first, then I don't need to shift at all, right? So which means that, let's say, if we are talking about the fewest shift, right? Then in that case, what we are hoping is that we are going to have 1105 come in first, and then 750, 740, 720, 660. Now, we only have room for top 5. So that is the sequence. Now, what about the rest? Well, the rest we don't care, because whatever sequences they come in, they're not going to replace the top 5, right? But of course, if you just want to be correct, okay, so maybe there is a specific sequence that is going to be in general true for any size of the leaderboard, and that is just going to be the things that is going to get you the sorted order, right? Which in that case, the last few is going to be 590, 510, 400. Okay, so that is the fewest case, right? Okay, now one of the things that we are going to look at then is what is going to be the worst case. So that is the highest or the most number of shifts. And that is in fact the cases when you have to get it in the opposite order, right? Which in this case, maybe you even start from the smallest one, right? So 400 comes, and then 510 comes, 590 comes, 660, 720, 740, 750, 1105, right? Now, how many shift? Well, the first one is not going to shift anybody, so 0. The second one is going to shift 1, because it's going to replace 400 as the first place. The second one has to shift 2. This has to shift 3. this has to shift 4, right? Then the one subsequent to that is going to be shifting 4 each time, because it's just going to go make its way all down to the top, right? So now let's start to look into how can we generalize this, right? And we're going to attach a value. Let's say that we have the size of the top k, right? And let's call that k. And let's say that the full length of it, and let's say that is going to be n, right? And n is going to be the full length from the beginning to the end. All right, so now let's say in general, how many shifts are we going to have, right? Okay, so let's work out the simpler ones first, right? So we know that towards the tail end, we're going to replace everything that is already in the list. So which means that for each of these numbers, I'm going to have k minus 1 shift, right? Because if my size of the top k is k, top list is k, then everything that comes in after that has to replace everything inside, right? So now, how many of such shifts I'm going to have? Well, I'm going to have n minus k of them. I'm going to have n minus k of them because there are going to be n minus k numbers that are outside of the top k, right? And that's just the last few, right? How about the beginning? Well, the beginning, I'm going to have 0, 1, 2, 3, 4. I'm going to keep going until I get to k minus 1, right? So then you have 0 plus 1 plus 2 plus 3 plus 4 until k minus 1. So then what you're going to have is that you're going to have k over 2, k minus 1. This is basically arithmetic series, and you would have done this in discrete math or something like that, right? Now, so now you have a particular number of the worst case that you're going to experience in terms of doing this, okay? And if you work out the numbers, then it's going to be some form of nk and k squared, okay? Now, at this point of time, I think we stopped short of actually looking at the complexity yet, because I think we will discuss that at a later point. But I just want to draw your attention to the idea that when we look at the algorithms, one of the things that we always pay attention to is how it is looking at the time, right? How many operations we're going to do, and we try to formalize that, quantify that, so that we know how many steps we're going to take, right? Now, this is in terms of time, and we do consider, let's say this is in terms of time, right? Well, the other thing that we also pay attention to is the concept of space. Now, which means that to solve this problem, you kind of like need to have some kind of nodes, right? So just like what we are doing here, we always need to keep the top k. So which means in this case, my space is going to be k. So meaning to solve the problem in this way, I need to keep track of the top k. I cannot forget it, because if I forget it, then I cannot solve the problem. So which means that to solve this problem, I need to make sure that I have this amount of time and I have this amount of space. And this is a requirement for me to employ this algorithm to solve this problem. In some cases, we may actually be able to solve problems in a better way, in a more efficient way, usually by increasing the amount of space. So if you, just like in real life, right? I mean, you kind of know the way to do something, but if you memorize them, then it's faster. But then you have to commit the memory to actually memorize them. So it's kind of like similar to a lot of algorithmic problems. If you're willing to sacrifice more space and memorize some of, more information, then generally you can solve problems in a more efficient way, time-wise. Okay, all right. Okay, so I understand there are a lot of different answers, depending on what you count as shifting, inserting, and so on. So don't worry too much about that. I think the more important thing is that you have some level of understanding of what it is actually working out in terms of the operations that are being done. Okay.